I'm Tim, as Kate said, and I'm going to talk about a bunch of work on models of language learning that I've been doing over the past 10 years, starting with my thesis, which Kate mentioned, and I guess that was all the typing, and moving through some newer work. I don't actually, so I give this talk, I did my PhD in the psychology department after being trained as a linguist, and now I work in computer science mostly. And so I'm used to talking to audiences with broad backgrounds, although I don't know that I have ever talked to an audience with this broad of a background. So I just want to kind of get a sense from people how many of you have a lot of background in language or linguistics or anything like that? All right, it's okay, about a third. How many of you are programmers, developers, computer scientists? All right, about a third. Sorry, there's no math, but I can fix that. You know, if you give me a marker. I probably should write on this though, huh? And anybody here a psychologist? All right, we have one. Good. Okay, good. So this talk is it's meant to be sort of generally accessible because I have to talk to all these audiences, and in general, intuition is the word of the day when you're trying to present difficult computational modeling materials. But I prefer to be sort of informal here. So please stop me if there's something that is unclear. Or if there's an example you don't follow and whatnot. Also, in terms of time, I could talk for 3 hours, but I'm not going to, I promise. But I could also talk for 45 minutes. If we get to a point which is a convenient stopping point, if it goes more slowly than we thought, I can just stop there, and we can, I can talk about whatever people are interested in offline. All right, so all of my research, well, not quite all of it, but most of my research over the past few years is focused on this issue of productivity, what I call productivity and reuse. This is kind of a rebranding. It's more traditionally probably known as computation and storage. So the basic problem that I try to answer across all of the projects I work on is why can some structure building processes, so why can some grammatical processes, grammatical rules, lexical items, morphology, these sort of things, be used to form novel expressions, while others can only be reused in existing expressions. So as is often observed in linguistics and the psychology of language, the most interesting thing about natural language is that it provides infinite use of finite means in Chomsky's famous translation of Humboldt. In other words, it gives rise, we can always create new word forms, we're constantly creating new word forms, we're constantly inventing new sentences. At any given day, you're going to hear sentences that have probably never been spoken before in the language that you're speaking. And this is the fundamental value of language that allows us to express an unbounded amount of concepts and thoughts. But of course, this gives rise to all kinds of puzzles of learning. So just to illustrate what I mean by these puzzles of learning, I'm going to give two examples. So first I'm going to walk you through some examples in the area of word structure or morphology, and then I'll show you some examples in syntax. So here's three English suffixes, ness, ity, and th. Now these suffixes are quite common in English. Ness is very common. So there's many words of cuteness, grandness, orderliness, pretentiousness, cheapness, etc. You can keep going. This means something like the abstract property associated with the adjective to which it combines. So this ness typically attaches to adjectives, not always. There's words like forgiveness, which isn't really attached to an adjective, but in general attaches to adjectives. There's many of them. And crucially, ness can give rise to new forms trivially. In fact, as a native speaker, you don't even recognize if there's a new form used in ness. Any issue of the New York Times will have multiple new words that have ness in them that have never been used before, etc. So we can say things like, this candle is pine-scented, and so it exhibits pine-scentedness. Now there's an ever-increasing proportion of the world which is familiar now with the word pine-scentedness, thanks to my talk. I encourage you to go out and use this word. So just for the purpose of this talk, I'm going to use this notation here to mean the rule that says we can add ness to an adjective to form a noun. So I'm going to use this sort of tree fragment notation. This is basically just says, this is just a variable that says any adjective can be put in there and it will be combined with ness, and the output will be a noun. Okay, so ness is fully productive. So productive, of course, is the term of trade in linguistics for grammatical processes that can give rise to new forms. What about this suffix ity? This Latinate suffix comes from itas in Latin originally, It's very, very common in English as well. Verticality, tractability, severity, seniority, nanity, electricity, and the list goes on. In fact, in any normal corpus sample, IDI is significantly more frequent than NES. However, it cannot be used to form new words. So pine-scented cannot be formed. You can't say pine-scentivity. I even applied the correct phonological changes to the stem there and moved the stress and whatnot, but it's basically gibberish. However, there are a few morphological contexts, so a few other suffixes after which IDI does generalize to form new words. So if I say something is basable, then you would say it has good basability. In fact, a colleague of mine was just doing some research that's only changed in American English, at least in the 50s. So the basableness would have been preferred prior to around 1955, but since then we tend to prefer to produce the nominal form of able with IDI. All right, so I'm going to actually use this notation to express that kind of rule. So this says something like, if I had a verb, I can combine it with able to produce an adjective, and then I can combine that unit with IDI to produce a noun. Now, I'm using this notation, basically, which expresses the internal structure of the derivation process. I don't mean to imply that I believe that, for instance, in the case of basability, our minds necessarily represent this structure, but of course, a particularly precocious child language learner could. And I just want to emphasize that all of this structure is sort of latently there in the data. And for a particularly powerful learning algorithm, such as a child, they could discover these things. And of course, there's this suffix th. So this suffix is more or less unrecognizable even to most native speakers, but it's actually quite common. It's warmth, width, truth, depth, etc. As you probably notice, it actually causes significant phonological changes on the stem. And there's lots of other ones that are totally unrecognizable, like sloth from slow plus the, and dearth from deer plus the, and these sorts of things. This one, of course, is completely unproductive. We can't form new words in it. So I picked cool and coolth here in particular because th does like to attach to monosyllables that end in an obstruent of Germanic origin. So cool should be good, though. I don't even know if in German there's a cognate of kulte or something like this. No. So in Dutch, for instance, there's a bunch of cognates we don't have in English. Like there's the equivalent of greenth. But we occasionally do see this used in print. So Daniel Deronda, George Eliot and Daniel Deronda wrote of the gleams and greenths of summer. But obviously this is poetic license, and everybody who's a native speaker immediately recognizes this. It's supposed to be funny or poetic. So again, I'm going to represent this with a little kind of rule that looks like this is not even a rule because, of course, there's nothing left to do with it. It's done. But I just want to express the internal structure such that I can point out that if I were a really powerful language learner, I might notice this generalization and I might over-apply it. And the point is, kids really do. All right. So I'm going to talk about some examples now about this sort of balance between productivity and reuse of structures in existing forms in syntax. So of course, in syntax and sentence structure, everything is much more productive than morphology. I mean, one of the key defining, it's actually not a defining, but one of the key properties of words is that they're memorized. And one of the key unproperties of sentences is that they're not memorized. That was a double negative. You take my point. But there are still pockets that look like this, even within syntax. So here's an example from the area of what's called verb argument structure. So verbs only appear in sentences with certain other noun phrases that express sort of the entities who are involved in the event expressed by the verb. So these are three verbs. They're all what are called dative verbs. They're verbs of transfer of possession. So give is the canonical dative verb. And give appears in two canonical constructions in English, one called the double object construction, so John gave Jane the apple, and one called the prepositional object construction, so John gave the apple to Jane. So these mean the same thing, and give can appear in both of these kinds of constructions. Most dative verbs can appear in both of these kinds of constructions, but not all. So if we take a verb like donate, before going on, I'm just going to express these kinds of generalizations using these sort of bigger tree fragments representing rules. So this says something like, give can appear with a subject, an indirect object, and a direct object, or it can appear with a subject, a direct object, and the indirect object ends up in this prepositional phrase. So these are just generalizations over those frames. So we take a verb like donate, however. At least my dialect, you can say John donated the money to charity, but John donated charity the money could only work if charity has a capital C. In other words, it's a person's name. So we'll express that again, that donate only appears in this particular construction. The other one is not available to donate. Somehow we're going to have to learn that because it means something extremely similar to give. So there's a question there, how we learn that it doesn't generalize in these contexts. This is an example I came up with after reflecting. This is a kind of obscure verb, to tender. As far as I can tell, I can ask the other native speakers in the room to tell me if there are exceptions. There are only two constructions in which tender appears regularly in English. To tender one's resignation and to tender payment to somebody. So these are really specific constructions, not very generalizable, not very productive, and very specific to even really kind of stereotype lexical items. So we have things like the tender, it has to have a possessive here, and a possessive pronoun when resignation, and the only real slot that can vary there is the subject. So here the actual direct object is fixed. This is sort of an idiomatic expression. All right, so we have these patterns like this of more productive, less productive, and least productive in both morphology and syntax. And these, of course, raise a bunch of questions. So first, how can these differences in productivity be represented? So I've already given you these little rule formats, so this is going to be part of the answer. But we actually need some kind of model of how the mind can even know that donate, how it can even prevent donate from appearing in the double object construction. And the second, of course, how can these differences be learned? And the reason that this is a major problem is that for any particular sample of any language, there are hundreds of thousands, if not millions, more potential generalizations that one could make that never get made. And so we have to have some sort of way of searching through this space and determining which ones are good generalizations and which ones aren't. There's a third question here, which I'm not going to give an answer to, although I have an answer to it. But we can also ask how these differences can be deployed during language use. So actually while I actually construct these sentences as I'm speaking, how do I actually grab these fragments of structure and assemble them? I have some work on that, but I won't get into that today. Okay, so there's going to be a couple main points. That's the sort of big setting of the talk. Those are the questions that I want to answer. Here's going to be some sort of take-home messages about how to answer them. So the first point is that we can actually solve these problems of productivity versus reuse by balancing a trade-off, optimizing a trade-off between productivity or computation on one hand and reuse or storage on the other with respect to some input data set and some set of prior assumptions about how the model works. I'm going to go into this in some detail. So this is, for those of you who are familiar, this is going to be a version of the standard Bayesian trade-off, likelihood prior trade-off. For those of you who know about minimum description length, it's roughly equivalent to that as well. It's a very standard tool, but it actually has in various models of inferential reasoning under uncertainty, but it has profound implications when we actually apply it to the question of what should be stored. The second thing I want to point out here is in a couple of these examples, I'm going to show how if we take more seriously the linguistics underneath these forms, then we can actually do better in terms of learning a good trade-off. So basically using better linguistic representations and more accurate ways of modeling the data lets us actually optimize this trade-off more efficiently. The third is I just want to point out this has surprisingly far-reaching implications for linguistic explanation. So there's a lot of, this is probably not the right audience to make this point, but there's a whole lot of baggage hanging around in various kinds of linguistic theory that can be gotten rid of once you adopt this sort of framework. I'll show you a few examples. All right, so actually I'm going to skip, I was going to say overview of the key results, but so there's a bunch of stuff that I've applied this to besides the stuff I could talk about today. We recently published a paper, which is the first paper ever, I think, that we built a model of lexicon learning. So we learned the set of word forms directly from the speech, from audio samples of, I think they're lectures, video lectures in the MIT lecture corpus. So we do completely unsupervised learning of the set of words in those, including their phonology and their morphology, just from the acoustics. I'm pretty excited about that, but I'm not going to talk about it much. There's also a bunch of work on phonology that I've done. I'm going to talk about English morphology mostly today. Some other things. In any case, I want to start off by giving the intuitions behind kind of solution that I want to propose to these problems. All right? So any questions there? This is a good point there. All right. Okay, so there's two big ideas here. So as I said, we're going to treat productivity and reuse as properties which are independent to representations. I'll say what that means in a second. And then we're going to infer the correct pattern of computation and storage by balancing our ability to predict forms of the data against prior simplicity biases. And this is going to optimize this trade-off I was talking about. So I'm going to walk you through some concrete examples of this trade-off so you can build some intuitions here about how this is going to work. But first, I need a model. You already have seen kind of the model I'm basically going to start with, which are these little fragments of tree structures representing linguistic rules. So that's going to be our formalization of the hypothesis space. And for the example of morphology, we're just going to have these tree-structured morphological forms. So we're going to start out with something like this. Is something familiar to people? This is a context-free phrase structure grammar, a little fragment of a context-free phrase structure grammar for English morphology. So this says things like, we usually think about this as a derivation, as a computational system that lets us derive the form of words top-down. So for instance, say we wanted to build a noun, so we might sample a rule that says noun consists of an adjective plus ity, and then this is going to correspond to deriving that part of the tree structure. Then we need to, of course, fill in the adjective variable now. So we'll sample another rule that says adjective can be expanded as a verb plus able. Now we have that, and then finally we need to fill in the verb, and we end up with this word agreeability. So I'm actually just going to think about these trees as sort of execution traces of the process of building word forms. Now our hypothesis space is going to be anything in this space of trees that can be stored and reused. So here's one possible set of hypotheses about how the word agreeability could have been stored in the mind of a speaker who first heard it. Of course, another possibility is this one. You can memorize the whole word. Here's a third possibility. There's a fourth. I'll leave it as an exercise. So the basic idea here is any contiguous subtree can be stored in memory and reused as a single rule from the starting, as if it were a single rule from the starting grammar. So the idea here is that if I store something like this, in the future I'm able to now generate a word form like that in 2 steps instead of 3. So I can do 1 and 2. So this hypothesis is very important to understand that what this means is that I now just have a single structure in memory that I can use in 1 step, right? The actual mathematical model uses it's a generalization of something called the adaptive grammars model. It uses some Bayesian nonparametrics like the Chinese restaurant process, the Dirichlet process. This is just so that people don't get angry that I don't cite them. So now I want to talk. So that's it for the formal model. I'm going to talk about there's obviously a lot of mathematical details missing there, but I just want to get across the intuition of what can be stored and what can be computed and how. Now I want to walk you through how we're going to actually do this trade-off optimization, how we're going to do the inference, or actually I'm going to walk you through some intuitions about that. So the idea here is we're going to use probabilistic conditioning to find a good balance between computation and storage. And we're going to find a set of computations which best predict the distribution of forms in a linguistic input, taking into account 2 prior expectations for simplicity. So far I've just sort of given you a space of representations. These are these tree fragments. Now I want to define some prior distributions on those that tell you, or 2 prior expectations that are going to give rise to an inferential system that we can optimize in order to learn good solutions for particular languages. So first of all, I want to just re-emphasize that we can think about these stored fragments of structure as predictions about the future. So in particular, if I've stored something like this, essentially what I'm saying is that I expect in the next sentence I hear, if that sentence contains the word, if that sentence contains a word using any of these pieces, that it is likely to contain agree, but agree might appear in multiple different contexts besides ability. So by storing something this way, I'm saying, oh, agree is a unit, which is going to appear in future sentences, but across many different contexts. Likewise, I'm predicting that when I see able and ity, they're more likely to appear together than you would expect by chance, and less likely to appear apart than you would expect by chance. This is what this says. And furthermore, I'm going to predict that when I do see ability, there will be quite a bit of variation in the verbs that it appears with. All right, so what are my two opposing simplicity biases that are going to let me build up an inference in this setting? So first, we're going to have a bias that just says, keep the number of lexical items that you have to store as small as possible and as simple as possible. So fewer, more reusable lexical items. This is intuitive. You're just saying, keep the amount of memory that you need for the system low. And the second is keep the amount of computation you need to build any particular form also low. So this is, and I'm just intuitively we'll just think about this as the number of discrete steps you have to take in order to build a particular form. So the first one is implemented by these Bayesian nonparametric distributions I mentioned. So this is just a kind of a standard technique these days for putting a sort of a bias where you don't know in advance the number of objects that you need to learn, but you want it to be as small as possible given the data. Of course, no smaller than possible, but as small as possible. And you want as small amounts of computation. And actually, this just comes out of the math because there's a geometric decrease in the probability of any form because we multiply the probabilities as we build up things. I'll show you this in a second. So the best way to illustrate this is just with an example. So imagine that I'm the child learner and I hear these four words spoken: agreeability, agreeableness, countability, and then I hear agreeability again. So here's my data set that I'm going to try to learn from. So I'm going to walk you through three kind of extreme examples. So here's one extreme example. Here's if I hear those words and I maximally decompose them into their component morphemes. So here these words are maximally decomposed, and the morphemes are sort of the minimal sized units that are basically, in this case, equivalent to the underlying rules that in the context-free grammar. So in terms of computation per expression, I'm going to have to make several computational steps in order to build each form. And because I assume that that this process, that the probability of this overall form is just the product of the probability of each of the pieces that you use to derive the form, as you make more computational steps, that probability goes down very quickly, of course, because probabilities are numbers between 0 and 1, so that approaches 0 exponentially fast. Never gets there, but it approaches it exponentially fast. So if I make more steps, it's going to be costly. The probability of the forms is going to go down. On the other hand, this may be compensated for by the fact that these individual chunks are highly reusable. Right? So now, as you see in this corpus, IDI appears in these three places. So if I make the further assumption that the probability of each chunk is proportional to its frequency in the input, then having these smaller, more abstract forms means that each of these individual numbers can be higher, right? And so what this means, of course, is that if these numbers are close to 1, then the rate at which this falls off is still exponentially fast, but much more slow than if those are close to 0. So I have more sharing across expressions with small abstract fragments, but more computation per expression. Okay, well here's the opposite extreme. So if I store the entire word, of course what's going to happen here is that it's going to be very cheap to compute any particular form. I just retrieve it from memory and I'm done. However, I'm going to have less ability to share across expressions. So here we see that I only can share these two across these expressions. I can only basically share exact repeats of whole forms. Now, of course, what you want to find is the combination that's just right. So in this example, of course, it's non-accidental that I chose the words that had this form with my running example here. So I can now derive these words in 2 steps, but I have as much sharing as in the first case. So we want to go ahead and search for solutions in this solution space that manage to optimize this balance. So we want to kind of find this sort of optimal point where, on one hand, more computation is predicting more novelty and more variability in the input. On the other hand, more reuse is predicting more repetition in the input. And there's going to be a kind of sweet spot, which is the best answer solution, and hopefully the one that explains a bunch of linguistic phenomena. All right. So that's the extent of my presentation of the actual modeling ideas. I'm happy to talk about the actual details to any particular degree of depth that people are interested, but are there any questions before I go on here? Okay, so now I'm going to talk about some results in English, derivational morphology. Does everyone know the difference between derivational and inflectional morphology? Yeah, okay. So inflectional morphology is things like case endings and plurality marking and verb conjugations, things which are typically obligatorily marked in sentences. You know, if you have a dative context, you know, you have to have dame if it's masculine and whatnot. It has to be marked. Derivational morphology refers to word structure which is optional and typically does things like changes the meaning or changes the category. So for instance, these are affixes like ness or kite, or these things, you add them onto an adjective and they create a noun, and it's purely optional. It's just if you need a noun in a particular position, unlike things like marking the past tense or something, which is obligatory, obligatory in past tense contexts. So I have a bunch of results on it. Inflectional morphology, I find inflectional morphology kind of boring, and I think the derivational morphology stuff is more fun, so I want to talk about that. So before I do that, though, I have, when I present these results, I sort of systematically compare the modeling framework that I've developed here with a bunch of other models that I implemented that are supposed to represent other theories that have been proposed of how this stuff works. And so I'd like to just go through these four other models right now, so that as I compare the results from my work to these, you have a sense of where it lives in this space. So there's five formal models total. They capture various historical proposals from the linguistics and psycholinguistics literature. Otherwise, they're minimally different. I try to keep things carefully matched because I want to know why my model is better, not just that it's better. So they all take the same inputs and the same underlying space of representations. So we're always going to be dealing with these trees, and incidentally, they're all state-of-the-art probabilistic models from natural language processing. So for those of you who know some NLP, you'll probably recognize most of these models, although I'll present them from a slightly different perspective. So the first model is what I call the full parsing model. So this is just the model that always stores just the minimal size units and never does any storage of bigger chunks. So this model is basically a non-starter in morphology, of course, because, as I said, one important fact about words is that we memorize them. And so if you were mandatorily decomposing every word, then you could never, for instance, not generalize warmth, and that would be bad. But it's useful to present this model as a baseline. So I'm going to essentially treat this as a baseline. The actual particular mathematical model here is something called maximum a posteriori multinomial Dirichlet context-free grammars, which is basically just a standard Bayesian context-free grammar. All right, so then naturally, another model I'd like to compare to is the full listing model. This is where you actually memorize everything. Now, importantly, this is not a non-starter for word structure. In fact, this is pretty close to the truth for word structure. And many important linguists and psycholinguists over the years have proposed something like this, some variant or another of this, as a model of how we learn words. Now, the important thing, of course, is that every model of word structure has to be able to generate new words. So there's no such thing as a list-only model. That doesn't make any sense, because had they had fancy Bayesian statistics to combine with linguistic models back then, I think this is a pretty veridical implementation of that idea, sort of updated. It's actually the actual model is something called the maximum a posteriori all-adapted adapter grammar. But one other thing I want to point out about these two models is that's useful for intuitions later, is that roughly speaking, these models are all going to estimate the probability of these chunks in different ways. And roughly speaking, to a first approximation, the full parsing model, which maximally decomposes all the words, is going to treat these probabilities as roughly proportional to their token frequency, which is, people know the difference between token type frequency? That's literally the number of times each of these chunks appears on the surface, like the actual count in the corpus. The adapter grammar model, the full listing model on the other hand, is going to generally estimate chunks based on their type frequency. So type frequency, a word type is just it's just a word. A word type is like dog, a word token is like every instance of the word dog. And so the type frequency is the number of different contexts a particular word appears in, not the number of instances of that word appearing in the context. So for instance, the type frequency of a suffix like ness is the number of words that end in ness, where you count each word once, don't count the fact that business appears 50,000 times or something. You just count it once. And so roughly speaking, the full listing model is going to estimate these things based on their, so like for instance, it'll estimate ability based on the type frequency, the number of words that contain ability. This is going to become important later on. There's been probably like every 2 years somebody in the literature proposes type frequency as a way of estimating productivity. Don't be fooled; it doesn't work. But it sort of comes close. It comes close a lot of the time. So I'm going to explain why that's sort of true. All right. All right. Then the third model here that I'm going to compare to is what I call an exemplar-based model. So in the concept learning literature in psychology, there's been a big debate about how to represent concepts, like bird or truth. And one of the big elements of this debate has been a debate between what are called prototype theories, where there's kind of a canonical representation of a bird, something that looks like a robin or something, and there are exemplar-based theories where instead of trying to extract kind of a idealized prototype for a concept, you actually just store all the instances that you've ever observed and then take some kind of average over that set. And so in linguistics, we can kind of do the same thing. So there's a framework developed by Remco Ska and Rens Bots in Amsterdam called data-oriented parsing, where when you see a sentence structure like this, you actually extract every subtree that's possible, and every possible way of carving up the sentence, and then in the future you try to use all of those when you parse a new sentence. And I tried to draw, it's hard to draw this of course, but I tried to draw this with these sort of multiple layers of overlapping colors, showing that this model stores the minimal size units, it stores the maximal size units, it stores all of them in between. And it tries to hedge its bets kind of over all of that. So DOP there's no, as far as I know, no one's come up with a Bayesian, a generative formulation of DOP, so there's a whole multitude of frequent statistical estimators for assigning probabilities to these particular units. You have to give a way of assigning probabilities since you can't just count anymore because there's multiple overlapping ways of deriving each form. And so I just picked the original one. I wanted to compare to DOP, so I had to pick something, and I picked the original one, which is data-oriented parsing 1, which just sets each tree fragment proportional to its token frequency, its surface frequency. And I picked this one, the equal node estimator, which is, as of today, the currently best version of this model for parsing natural language syntax. All right. And finally, I'm going to call the framework I've been sketching the inference-based model. Now, why I call this an inference-based model is because all three of these earlier models can be understood as having a deterministic rule about storage. They're probabilistic models in the sense that they assign probabilities and represent ambiguity, but what they store is just determined in advance. The full listing model stores the biggest chunks all the time, the full parsing model stores the smallest chunks, and the exemplar-based model stores all of them. In the intermediate ones as well. The inference-based model can do all of those things except that it commits to a particular derivation of every sentence, every word in this case. So the point here is this, that I actually am going to treat, in the terminology of the statistical terminology, I'm going to treat the particular way of carving things up here as a latent random variable. But the idea here is that there is a right answer, you just can't observe it. As opposed to trying to hedge across all of them or always picking just the smallest or just the biggest. Right. Oops. Okay, so I'm going to compare to those. Those are the four models I'm going to compare, or five. I guess there's two versions of the exemplar-based model. So there are in my thesis, I looked at two areas. I looked at the English past tense, which I don't know if any of you guys are familiar. In the 90s, there was a gigantic debate in linguistics and psychology that centered on the past tense. Some folks had introduced some neural network models that purported to be able to learn some things about past tense overregularization by children, so how children say goed instead of went. And Steven Pinker and colleagues came back, and there was a huge, came back against this sort of connectionist approach, and there was a huge debate in the field, and Steve was on my committee, so this made it into my dissertation. It's actually, as far as like linguistic systems of the world, the English past tense is not the most interesting one. It's actually English morphology in general is not super fun. I prefer Arabic, but so I'm just going to give you a brief overview of what I did here, and mostly I'm going to talk about these derivational morphology things. So again, just to remind you, the English past tense is an inflectional system, and derivational morphology, which is things that have to be obligatorily marked on verbs and nouns, etc. Derivational morphology, of course, are these more interesting morphemes that you can use to kind of form new words with new meanings, new categories. Right. So okay. So there's some general points about all the simulations I'm going to report here. One is that, you might have noticed that I've given these trees, like for instance, I give the tree for warm. This already assumes, of course, that, say, the learner has been able to segment that into warm plus the, which is a non-trivial problem in itself. So I just want to warn you that all the inputs to all these models are trees. I have other work on segmentation of the actual phonological strings. I actually think the right model is a joint model that does both simultaneously, because these things can feed and bleed each other. But for the purposes of this work, I wanted to focus just on the storage computation trade-off without worrying about the hard problem of segmenting. And so the inputs here are trees. There's no phonology or semantics in any of this. So when I write warm plus the, that's just a convenience, so you can remember that's the word warm plus the. Those might as well be integers at the bottom of the tree. I'm just treating those as like, they have an identity and that's it. I'm not modeling the actual phonological structure here, nor am I modeling anything about meaning. So anything that we learn here is just going to be straight up from the distribution of co-occurrences in the data. That's the only kind of evidence that's available here. Now, it's often been argued in linguistics that lots of things aren't learnable from purely distributional evidence, and so when we show that they are learnable, this is important because for the most part, the actual phonology and semantics are correlated. So unproductive morphemes are also give rise to obscure words like sloth. So that's very common. So sloth is from slow plus the, but it's no longer transparently related to slow. You usually have to tell people. This is very common. So in fact, if we actually modeled the phonology and semantics, this would provide an additional signal that should make learning actually easier. But in fact, we can actually get most of this just from the distributions of forms in the data. Furthermore, I'm going to actually err on the side of decomposition, meaning any place in any one of the inputs that there was something that could be a morpheme, I've segmented it. Because if I didn't do that, then of course the problem is done before I even start modeling. So I want to see I'm going to basically start. This is kind of an implemented thought experiment in a sense, right? So I'm going to say, okay, suppose that I started from the position where I over-segmented everything. I made everything productive. Could you take the input distribution and learn to constrain that productivity back down to the correct pattern for your language? Right. So this is what I call an idealized learning study, not an actual model of child learning. This is sort of an idealized learning study designed to examine what information is there in the input corpus that could be exploited by a particularly efficient learner. And so finally, you'll see I do a bunch of different things with the outputs. So the outputs of these models are just grammars, which means they're just computational processes that can be used to generate forms, which means that I can ask all kinds of interesting questions about them. I can treat them as sort of experimental subjects and run experiments on them and this kind of thing. So, all right, so here's an example of the maximum decomposition. So here, this one is a kind of interesting example. So there's this combination, ation in English, which is actually fairly productive. We stick it on things. You have words like formation. It's almost in every single linguistic theory I've ever seen treated as a single affix. This is despite the fact that there's plenty of words ending in ate, like defenestrate. Sorry, that's for aficionados. And shun, like regression. But there's lots of words that end in ation where the ate form doesn't exist. So formation is an example. There's no word formate. Considerations like this cause most linguists to actually treat this as a separate affix itself, separate from yun or ate. But of course, this is begging the question in the case of my work, right? So I have to not do that because this is precisely what I want to learn. And in particular, this example will come up again. Okay, so first let's look at just the productivity learned by the various models of a bunch of English derivational suffixes like these. And then I'll talk about some phenomena having to do with combinations of suffixes. Okay, so there's been a ton of proposals in the literature about how productivity should relate to frequency. So basically, when you get some input corpus, how should you count things in order to determine which forms are productive and which aren't? There's been a large number of proposals. One's based on type frequencies, which I mentioned. That's the number of distinct forms that a suffix appears in. One's based on token frequency. That's the number of instances things appear on, usually with something else involved. And one's based on various notions of dispersion. So like, for instance, how phonologically varied are the stems that a suffix appears with, that kind of thing. So one observation that's been made is that productivity is actually correlated with a set of mathematical probability distributions, which are called large number of rare event distributions. I just want to get across a little bit of an intuition here, which is that the crucial evidence that something is productive is the productive use of that thing. So in other words, if I wanted to convince you that ness is a productive morpheme, I should stand here and make up words in using ness, or I should try to work one into every sentence. But they should all be new. And in fact, if every one of them were new, you'd be really convinced really quickly. On the other hand, things can only be new once. So as soon as you use it the second time, then it's going to start counting against the productivity of that morpheme. Okay? Because you don't know, for instance, as a child learner, hearing a word like, I don't know, business or something, if that's the only word you've heard, and you've heard it 5 million times, then you have no reason to believe that it's not just a single morpheme without any internal structure. Okay, so the basic trade-off that we've been talking about also kind of arises in this sort of frequency distribution sense, where the best evidence for newness is newness, or for knewableness is newness, and the best evidence for storage is repetition. So the distributional consequence is a large proportion of low-frequency forms. Okay, so this is something that has been observed before. There's a Dutch morphologist who has a theory of productivity based on, well, I'll talk about this in a second, so I'll skip it now. But so unfortunately, there's no real quantitative data on productivity judgments, like large-scale databases where we actually ask people how good wugness is or how good wuggity is, this kind of stuff. I like wuggity. So what I did here is I actually just generated the 5 most productive morphemes according to each of the models under the training set that I'm using. And so this is going to be kind of a qualitative analysis, but it's already plenty to get rid of all but one of the models. So these are the 5 most productive affixes. So the notation I'm using here, by the way, is the affix and then the input category and the output category. And there's a good reason for this. It's because wow, that's interesting. I never even noticed this one before. Anyway, the reason for this is that there's many of these suffixes which have the same surface form, but they're actually different suffixes. So there's like, in English, for instance, li is the adverbial suffix, so you say things like quickly, but it also is a suffix that forms adjectives from nouns, as in like womanly. And those are distinct suffixes. Those have somewhat different meanings and definitely different uses. So here are the top 5. I don't expect you to read through all of these, it's kind of dense, but let me just draw your attention to a pair of suffixes. So probably ness or adverbial li is probably the most widely discussed productive morpheme and derivational morphology in English. And of the 5 models, only the inference-based model actually puts ness in the top 5. So the others don't have it at all. By contrast, every single other model treats yun, this is not Asian by the way, this is yun by itself, as either the most productive affix in English or the second most in the case of the full listing model. So this is absolutely crazy because this affix so this is basically predicting you should be able to take words like eat, and the act of eating is an eachen, or like at lunch there was much eachen, or this basically is predicting that you can attach yun on any verb, wakshin, these sort of things. I don't know how to pronounce it, but this is what's being predicted here. So what's going on? What's up with this? Why is this happening? Well, here are what are called the frequency spectra of Ness and Yun. So what's a frequency spectrum? So as along the x-axis of these plots is the frequency on a log scale of words that end in those affixes. So there's, and then these are sort of binned. So how many words appearing with frequency 1, how many words appearing with frequency 2, up to, extremely high frequencies, okay? And so this is basically the number of words at each frequency that appear for that. So this is basically showing you if there's a lot of words that appear infrequently or many words that appear very frequently, etc. And here is an estimate of the, this is, I guess here I'm using actually a probability, so it's a normalized estimate rather than the raw frequency. So this is the proportion of words appearing at each of these frequencies out of all the words that end in yun. And what you can see here is that for yun, it's roughly log normally distributed. So there's like a nice kind of normal distribution looking thing here. There's some words that appear extremely frequently with yun. So like there's one apparently that appears just over 22,000 times in the input corpus. There's many that appear only once. But the actual shape of the distribution is, a few appearing a small number of times, a few appearing a large number of times, and most appearing kind of in this middle range. Ness, by contrast, is very, very different. So first of all, note that Ness is way less common than yun to begin with. So even the most frequent one only appears about 3,000 times, as opposed to about 22,000 times. However, most importantly, however, is look at the peak right here at the number of words ending in Ness that only appear once. Now, this, of course, is exactly the characteristic you expect to see of a productive process. So Ness is being used to make new words every time somebody sits down to write a news article. They might accidentally use a new word in Ness without even realizing it. And so it gives rise to distributions of this form. They're peaked at 1 and swiftly fall off, okay? So why are the models behaving the way they do? So the inference-based model actually pays attention to this fact, that there's a high proportion of low-frequency types. However, the other models all get tricked by either one of two factors. So for the full parsing model, remember I said that it estimates the frequency of something, the productivity based on the surface frequency. So in other words, it's estimating the productivity by just taking the sum of all these frequencies. That's an extremely productive morpheme in that sense. And the full listing model actually goes on type frequencies, right? So in fact here, these are the surface frequencies, but there's also quite a lot of distinct words that end in yun. So the type frequency is also extremely high. In fact, way, way higher than this, because there's just way more words in the samples that have yun at the end. And so the full listing model is getting tricked by the high type frequency. The other two models, I won't go into why, but they are based on the token frequencies as well. Basically, they go with the token frequencies, kind of smooth in different ways. So what's the point here? So the point is this, that it's the distribution of tokens over types that matters, and it's actually the occurrence of a large number of rare events. And in particular, people keep proposing these type frequency-based estimators, and the reason that they keep proposing them is they usually work, because if your token frequencies aren't too high, then type frequency is a good estimate of the number of rare events. However, you can counteract any degree of type frequency by making the token frequencies high enough. Right? So if I have a million words that appear with a certain ending, if each one of those appears a million times, not productive. This is probably unlikely, but this is a trap that the literature keeps falling into. So I just want to point out that there's a pretty well-known theory, mathematical theory of productivity based due to a guy named Harold Bayen, which introduced these measures called script P and P, script P and script P star. And they're basically estimators of productivity which are based on the proportion of frequency 1 words in the input corpus. So you basically just look at the proportion of words ending in some suffix that appear once and divide that by the total number of words appearing with that suffix, and that's his estimator of productivity. There's various mathematical derivations of this. It can be derived from something called good Turing smoothing. It's a special case of good Turing smoothing. You can also derive it as the derivative. You can derive it as the rate of change in vocabulary size under a very simple model of independent word sampling. But fundamentally, this is just a heuristic. It was introduced by Bayes. It kind of works. He said, hey, look, if you just look at the proportion of low frequency items, then it works. And what I can show here is that basically the model gives the same predictions as Bayes for the cases in which it gives predictions. What time is it?
4 minutes of 2.
Oh, okay.
4 minutes.
Good. I'll stop after this. I guess.
All right.
And so Bayes here. So this is just showing that the Bayes model predicts roughly the same kind of levels of productivity as my model does. His model only works for single affixes, and unlike in my model, the assumption that the number of rare events is what matters is not anywhere directly encoded in the model. All that's encoded in the model is the process of structure building plus this inference. It's just a consequence of that what's going to matter is the number of times something appears infrequently. So you can see my model is a way of deriving actually Bayes predictions. Okay, I can finish this last bit, I think, in about 5 minutes. Is that okay? All right. So morpheme combination order. So this stuff is this stuff is fun. So I want to go through it. So one of the cool things about derivational morphology that doesn't occur in inflectional morphology, of course, is that we have words with multiple morphemes in them. You have words with like internal structure, so things like agreeability and affirmation. What this means is that there are many possible combinations of things like combinations of suffixes. So now one very famous observation in linguistics is that of the various, so obviously if I give you a couple of suffixes and you start stacking them up, the number of possible words increases exponentially fast. Just multiply the number of suffixes possible in each stop, it goes up very high. But of the many, many combinations of suffixes that could appear in words, most of them don't. And that's just true in every language, even taking into account things like categorical and phonological restrictions. So there's a famous study by Nigel Fabre in 1988 where he looked at 43 suffixes and after eliminating things for various linguistic reasons came up with 663 possible pairs that should be attested, but only 50 existed in his dictionary sample. There are, like this has been the focus of an enormous amount of linguistic theorizing, most of which is not very effective over the years. There's been one observation that's been made though, which is there's a relationship between these ordering generalizations and productivity, which is that more productive things tend to appear outside of less productive things. So if I have, let's think, what's an example here? If I have ubble, which is, that's a bad example because it's one of the exceptions. But in any case, take my word for it. I call this the productivity ordering generalization. I just want to point out, so people feel like there's whole books written on why this is the case, but it's trivially clear why it's the case in this setting that I've sketched. Does everyone already see it? Should I go through it? I'll go through it. It's a necessary consequence, right? And the idea is simple. Look, so in this setting, unproductive morphemes are stored together inside of words. That's what it means to be unproductive, is that if I mostly occur stored together with a stem, then I'm an unproductive suffix. More productive suffixes have variables in them and are happy to attach to any structure of that type. So all else being equal, if I just sample from that system, then I will get suffixes that are productive attaching both to monomorphemic stems, but also to morphologically complex words that have less productive suffixes in them. So this just falls out of the way the system is set up. So people have observed this and tried to explain it, but it just comes under a very simple sampling-based kind of story here. All else being equal, a productive thing is happy to attach to a morphologically complex form that has an unproductive thing in it. However, there's a number of very problematic cases where this is reversed. So ability, Haitian, istic, and mental and these, like, honestly, there's like many papers going back to the 70s on these things, trying to explain why they should exist. And in particular, I'm going to look at a pair of cases, and then I'll wrap up. So these things are called paradoxical. They've been paradoxical under every theory that's been proposed, all the way back to like level ordering theories from the 70s. But the basic idea here is that "-ity", as we've talked about throughout, is not a very productive suffix, but "-able" is a very productive suffix. Why does "-ity" appear after "-able" in new words? So this is the question. And these are other examples. So "Asian", we already saw that a couple times. "Istic" and "mental" are other examples of this. And there was a particular pair of cases which has been studied in detail, which is "-ity" versus "ness", after two other suffixes, which are "-iv" versus "-able". So there's been some experimental work here. So it turns out if you make up new words like "depulsive", and then you ask people if they prefer depulsiveness or depulsivity, they prefer depulsiveness. And if you make up a new word like "remortable", and ask people if they prefer remortability or remortableness, they prefer remortability. So you have a perfect cross here, where in one case you prefer the actual productive suffix, which is "ness", in the other case you prefer the unproductive suffix, which is "-ity". Now, of course, what I'm proposing is going on here is very simple, that these cases that look like exceptions are only exceptional because the two suffixes are memorized together as a generalizable unit, basically operating as a single suffix. So here's some results on that. So this is, I basically performed this experiment on the models. I gave them novel words that ended in "-iv" versus "-able, and this is when the preceding, this is what the data is going to look like. So the red bars are when the preceding suffix was "-iv, and the blue bars are when the preceding suffix was "-able, and that's preference for "ness", and that's preference for "-ity", and sorry, I already said that. And here are the results. So the full parsing model, which tends to go with the token frequency, always prefers "-ity", which is more token frequent than "ness". The full listing model, which prefers type frequency, tends to prefer "ness" to "ity", which is more type frequent than "ity". The two exemplar models go with the token frequency, and then you get the correct pattern under the inference-based model. And here's a bunch of examples. I just did a search that took about 3 weeks of every possible sequence up to length 3 of suffixes in English. And here's some ones that are predicted to be highly generalizable as units under the model. And the most generalizable one is Asian. That's reassuring. But there's other interesting ones in here too, like things like "-ifi", "-ate", and "shun", which of course is not pronounced like that. It's pronounced "ification", showing that it must be stored in some sense. And just as a last cool thing that I told you about, that model that learns the lexicon from just raw acoustic data, one of its most important units that it learned is Asian. So this is completely unsupervised, just from spoken language. We also recover these same units, so that's even better evidence that this is true. So, all right, so I'll stop there and
Thanks.
yeah.